Hi, this is Justin Rutledge, and I'll be providing a brief overview of the results from the course project for Programming Languages for Advanced Data Analytics. So I'll start off by saying the goal of this project is to derive some information or find some insights valuable for software development and software design to provide more secure software as a result. And so we'll start off by talking about some key terms and some of the data sets that I've used. So first thing that we need to be familiar with is the National Institute of Standards and Technology, or NIST. This is the United States organization meant to maintain technical standards. It started as a physical science lab back in, I think, 1901. And today their mission is basically to be the source of measurement standards for the United States. And lots of their work is used around the world, and they're plugged in with international standards organizations as well. From NIST, we have the National Vulnerability Database, or the NVD. This contains a record of hundreds of thousands of vulnerabilities exposed to software products within the US and products that citizens of the US may be using. This database contains records that are called CVEs, or Common Vulnerabilities and Exposures. Each CVE record also connects to other standards from other organizations, the Common Weakness Enumerations, which is a list of software or hardware weaknesses. That's maintained by the MITRE organization. And then each CVE record also has a CVSS, or a Common Vulnerability Scoring System score. This score is meant to indicate the severity of the vulnerability or the exposure, the CVE basically. There's a lot more within a CVE record, but these are the only items that are really necessary for us in order to understand the work that I've done. So to recap, a CVE record has a description, a textual description of what the CVE is. It has the CWE, or the Common Weakness Enumeration. This is like the category or the type of weakness that it is. So a CVE record might be, say, Apache Server version 3.24 has some problem with it, right? Some very specific problem. And then the CWE could say, okay, it's vulnerable to SQL injection, for example, the broader category of weakness that it is. And the CVSS score is going to be the specific severity of that vulnerability for that specific system. So with Apache Server version, whatever we said, it would be the severity assessment of that vulnerability. That being said, I'm using all 100,000 plus records from the National Vulnerability Database. This was over 2 gigabytes of JSON data that I've converted into CSV data. But we'll go ahead and get rolling. So the methodology here, yes. So the majority of the data that I've used, I pulled from 3 different data sets, but ended up using primarily data from just this National Vulnerability Database. In each CVE record was its own JSON file. And so I parsed through hundreds of thousands of JSON files, wrote some Python to do this, and converted it all into a series of pandas data frames, and then into a CSV file ultimately, pulling out and extracting only those fields that mattered, which were indicated in the last slide. So the first visualization that we've produced here is we're looking at a trend of CVEs over time. I wanted to look and see, hey, of these vulnerabilities and exposures that have been discovered since 1999. So these records began to be recorded in 1999. So we've only been going for about 25 years now, but we've seen significant growth. And on average, the number of CVEs discovered annually doubles every 10 years or so. So we're seeing a huge trend upwards. That can be explained partially because information technology is more prevalent today, and partially because there's a greater effort to record and make note of vulnerabilities in software today versus previous years. The next visualization for the exploratory analysis is distribution of CVEs by CVSS category. This is interpreted as the severity rating of the CVE, of the vulnerability. So we can see that the majority of vulnerabilities that we have a CVSS score for are medium or high. Very few of them are critical or low comparatively. And so we kind of have, it's very, very small here, but kind of a normal distribution. We can kind of see the kind of a bell curve here, even if it's just only 4 bars. But what this is really saying is that most vulnerabilities out there are not critical. Plenty of them are high, but the vast majority are rated as medium severity. Now, this should be noted that the severity is not a risk assessment, because this does not indicate the frequency of how often this vulnerability is exploited or could be exploited, just indicates the severity of what would happen if it were to be exploited. One more thing to note on this before we move on. You notice there's over 270,000 CVE records in the dataset, but here it caps out at about 35,000, and 35,000 times 4 is not anywhere close to 270,000. The difference there is that the CVSS score can be explained by the fact that a CVSS score is not present in every single CVE record. It's not a requirement of the reporting process to have a CVSS score, but we're seeing more and more CVSS scores applied to CVEs in recent years, and CVSS scores weren't even a thing before, I think, 2005 or something like that. So the first few years of CVE records, there was no such thing as a score for it. Here we see the CWEs, or the weakness categories, right, the weakness enumerations, contributing to high severity CVEs. So the top 10, right, the top 10 most prevalent among the CVE dataset, and only those that fall in the high severity category. So 7.0 CVSS score to 10.0. So they'd be high or critical. And one thing that we can glean from this information is that there are three, well, really there's two that stand out more than any of the rest: CWE 79, CWE 89. This is the first time we get some meat to our analysis. We see that cross-site scripting and SQL injection of those high severity CVEs that the categories are most prevalent and the weaknesses are most prevalent, these are the top two: cross-site scripting and SQL injection. This should come as no surprise to any web developers, since there are so many tools and frameworks out there to help prevent this kind of thing. But what we see from the CVE data is people aren't using it reliably, or for a lot of these records it didn't exist when the vulnerabilities were out and not remediated. But it's still something to be aware of to make sure that during development these items are noted. The CWE 20 is improper input validation. So I noticed CWE 121 doesn't have to do with the same kind of thing as the rest of these, but handling user input in an application or a website seems to be one of the heavy hitters to reveal a high severity vulnerability. Next visualization is the trend of top CWEs over time. So what I've done here is I've charted per year the number of CVEs for each CWE of the top 10 most prevalent. So the same 10 that we looked at the last slide. So we see a huge spike after 2020. It's the most notable thing here. Huge spike of CWEs 79 and 89. Again, cross-site scripting and SQL injection. So this is consistent with our last look at things. Finally, something really interesting here. We take this one step further, and I put together a heat map using Seaborn, the Seaborn package, in coordination with Matplotlib, for CWEs and CVSS scores distributed for their distributions across all CVEs for the top 20 CWEs. So we're expanding that group of CWEs from the last couple of charts to 20. And we're taking a look and we're going more granular rather than just medium, low, medium, high, or critical. We're looking at 0.5 degrees of granularity within the CVSS score ranges. And a couple of notable things here. We can pull out some other really interesting CWEs across all of the CVEs for out of bounds write, use after free, which is basically trying to reference memory that's already been deallocated, cross-site request forgery, and heap-based buffer overflows. Now, some of these may not be as severe as the other vulnerabilities, or across all the vulnerabilities that we've analyzed here, but it's worth noting that if we look at the data in a different way, like across a heat map, we can see vulnerabilities, we can see weakness categories that are still really prevalent and should be remediated probably at the top of mind of developers during software design more than others, even though they may not be as severe, just because they're so common. And finally, a note on predictive analysis. I used a random forest classifier to predict CVSS severity class, critical, high, low, medium, based on the description, the textual description, and the CWEs for each CVE. And to achieve this, I used I basically vectorized, tokenized the text data using a package from scikit-learn, and I used one-hot encoding for the CWEs, CWE categories, and I combined those vectors into a single consolidated one, and fed that into the random forest classifier from scikit-learn, and it produced these results as the classification matrix. The precision score indicates the positive predictions given the severity result. It's the accuracy of it. The recall indicates how well it identified actual positive cases. So as you can see, it kind of got the formulas there. So precision is true positives divided by true positives plus false negatives, and recall is true positives over total positives plus false negatives. And the F1 score kind of combines those two metrics into a single one. So it's a good gauge of accuracy that takes into account both false positives and false negatives. As we can see, the model here did a pretty good job, an above average job overall, but it did a below average job predicting critical vulnerabilities. So in more cases than not, it would encounter in the test data critical CVE and look at the text and look at the CWEs assigned and think that it's either high, low, medium, or unscored. But it did a pretty good job with the rest, above average. I chose random forest classifier. I chose to use this because it could run relatively quickly on a very large amount of data, of text data. I think that other models would be better suited for this, things that could do better natural language processing, tokenization of the text data, and representing that in like vector space a lot better. But we would need more computing resources to really take advantage of that, given the size of this data set. Finally, I think there's a lot more that could be analyzed here. There's a lot to be done in this field, but I'm happy with the results that I've found, and I think that this could be useful to anybody as a starting point for looking at a quantitative analysis of cybersecurity towards software development.